So here we have the mechanism now. So just now we already mentioned how electrophile is formed. So now electrophile is formed, and we start going through the electrophilic substitutions. So first of all, the electrophile, as you can see here, the electrophile, we go and attack the benzene ring, the delocalized electrons. But we can't draw the arrow to the circle. We can't draw that because there is a rules to follow. The curly arrow that you draw, right, must be negative to positive. Okay, so although when you write, electrophile attack pi electron ring. We say electrophile attack it, but at the end we have to draw arrow in the other way around. Must follow negative to positive, no? So accepting a pair of electrons from benzene. Okay, where's the electrons come from? There are 6 pi electrons that are delocalized here. So 2 of the electrons are taken by the electrophile for temporarily and form a covalent bond here. And 6 minus 2, now it has 4. It has 4 here. And 4 is not stable, not stable. And because of 4 electrons remain in the delocalized system, which is lack of 2, so it becomes positively charged or temporarily. Positively charged, not stable. And because of that, hydrogens will be removed, and heterolytic fission happens again. Hydrogen don't get any electrons, and it becomes H+. The electrons, 2 electrons in the bond are given to the ring, which is lack of 2. And it reforms a stable ring of 6 electrons after H+ goes away, and the electrophile just now remain as one of the part here, so they form a new structures. Okay, so let's see the words. Electrophile attack pi electron ring, accept a pair of electrons from benzene. So the benzene has lack of 2 electrons now. An intermediate positive species is formed. So it becomes positive species because 2 electrons gone already, and it becomes more positively charged. So in which positive charge is delocalized around the ring. So it's here in the ring here, more stable than a normal carbocation. Carbocation is carbon with positive charge. That is less stable. This is more stable, but still it is not too stable until it can remain as these structures all the time. So it will still changing to something else which is more stable. Okay, which is number 3. So proton eliminated. That means the H+. H+ is eliminated from positive intermediate. This is the positive intermediate. To restore stability, they remove the H+ so that the benzene ring of 6 electrons, 6 delocalized electrons is formed, and that is more stable. Okay, so the delocalized electrons are 6 electrons reform. So these are the mechanisms. And now let's see which reagent can go through electrophilic substitution. So we have the first one, halogenation. Benzene ring react with halogens. Halogen is like chlorine, bromine, iodine. Okay, so then they break down through heterolytic fission. Try to recall back the equation just now, where I said aluminum chloride will make heterolytic fission happen. The covalent bond in Cl2 break down. The bonding electron is divided in a way that is not fair. One Cl get nothing, another Cl get 2 electrons. So the chloride, the Cl minus, which get 2 electrons just now, will stick to the aluminum chloride. You know, aluminum chloride, right, have something special. This catalyst, aluminum chloride. It has empty orbital. So that's why the Cl minus will come here and form the Cl4 minus. It has empty orbital to accommodate the chloride. And then the other thing is Cl plus. Electrophile. This is the electrophile. So the electrophile will go through the mechanism as in here. The E plus is now Cl plus. Cl plus stick to the benzene ring. Cl plus remain in the benzene ring and kick out the H plus. Okay, so this is overall equation. Before you see the overall equation, we need to understand what happened to the H plus, which has been kicked out from the mechanism here. So it's here actually. The H plus that is kicked out from the mechanism will go and find the AlCl4 minus, which is originally a catalyst. Catalyst must regenerate at the end of the reaction. So the chloride just now, this chloride I will stick here just now. This chloride will go and combine with the H plus to form HCl, and catalyst regenerated. So this is where catalyst come out again. Okay, so they found HCl, So that's why you see one of the product, HX, something like HCl. Another product is C6H5Cl, for example. C6H5Cl. Be aware that originally is C6H6. Now one hydrogen disappeared. One hydrogen gone already, So it becomes C6H5. C6H5, and then replaced by chlorine, for example. Yeah. Then the hydrogen which kick up from HCl with the other Cl, the one that is negatively charged. Okay. So that is the overall equation. Something like C6H6 plus Cl2 becomes C6H5Cl plus HCl. Okay. Reagents, you can use dry Cl2 gas, pure Br2 liquid. No matter this or this, you will observe something. They try to avoid H2O. Dry Cl2 gas, no H2O. Pure bromine liquid, no H2O. So they don't want to have H2O. So then they will react with benzene ring. If H2O is there, we can easily predict Cl2 rather react with H2O rather than react with this. Because this one is not so reactive one, So we don't want H2O to be there. Conditions: room temperature and pressure. Catalyst: aluminum chloride. If you use chlorine, then aluminum chloride. If you use bromine, then iron 2 bromide or aluminum bromide will be fine. So generating electrophile. This is how they generate electrophile. Catalysts are electron deficient. This one, lack of 2 electrons to achieve octet. This is called electron deficient, lack of electron. Halogen carriers. So they carry the halogens. The catalyst will carry the halogen, so to form this halogen carriers. Form dative bond, drawing electron from halogen molecule producing X plus. That means they take the Cl minus, then the other Cl will form Cl plus. They are trying to talk about that. At the end, regenerate. Okay, so we move on this side. The second way to go through electrophilic substitution is by using This is called nitration. Nitration. Nitration means the nitro, NO2, nitro will go to the benzene ring at the end. Nitrobenzene. Okay, to make nitration happen, so we have to use concentrated sulfuric acid and concentrated nitric acid. Okay, so why so extreme? These two are strong acid and some more concentrated, very extreme already. So because this is unreactive. Okay, first of all, let's see how these two acids react with each other to regenerate electrophile. So which is here, generating electrophile, formation of nitrile ion. So sulfuric acid and nitric acid. Between these two acids, right? So obviously H2SO4 is stronger, because it is two hydrogen, diprotic acid. So stronger. So the stronger acid will act as acid, so it donate proton. So you see, it donate proton, become HSO4. It donate proton. Okay, so something like this. Okay, right. Try to write an equation at the side here. 2 sulfuric acid, they form 2H plus, then donate proton, right? Plus 2HSO4, hydrogen sulfate. And they go and find the nitric acid. So nitric acid look like this. Nitric acid look like this. So what happened is, here breakdown, and two hydrogen come here, and they form H3O positive. Okay, so that's why you can see in the generating electrophile information here, there is H3O positive, because two hydrogens and the OH, they found H3O positive. Whereas this part, they found NO2 positive. That is the electrophile. Okay, so you can see it in the notes also. The note just write down the equation without explaining much. So here I show how the breaking happens and how electrophile is formed. And electrophile will go through the same mechanism again. They will approach the benzene ring, form a new covalent bond, and then one of the H plus will come out, and at the end the NO2 can remain with the benzene ring just now. So the H plus, the H plus that come out from the mechanisms, where are they going? Or you can see here, they go and find the HSO4. You see the H plus, the H plus just now. Go and find the HSO4 together with the H3O positive just now. They all form back sulfuric acid, the catalyst, and H2O. Okay, so the H3O positive become H2O. This donate proton, and this one also give away the proton to the HSO4. So accept 2 protons and form sulfuric acid. Temperature 45 to 55 under reflux. So when we say reflux, that means we need kind of extreme condition to make these unreactive benzene rings form nitrobenzene. Okay, so now you can see the equation again. The H2SO4 is the catalyst. It regenerate at the end. If you don't want to write H2SO4 on both sides, just write on top of the arrow. It's just fine. Okay. Then the nitric acid break down to NO2 and H2O also there. H2O. So next one, alkylation and acylation. So alkylation, alkyl means, like CH3 is one of the alkyl. We call it methyl. C2H5. So let's say I write down alkyl. Alkyl is CH3, CH3 with a branch with a covalent bond, C2H5, propyl, C3H7. All these are alkyl. So alkylation means the hydrocarbon side chain is added to the benzene ring. So acylation is like COR that add to the, okay, this one I write properly, C double bond O. This is acylation. The R is the hydrocarbon part. Hydrocarbon part. COR stick to the benzene ring is called acylation. All this CH3, C2H5, C3H7 stick to the benzene ring is called alkylation. So now let's see the situation or the reagent here. So you can use alkyl halide to go through acylation. Okay, so for example, you can do methyl, right? Methyl, the reagent can be CH3Cl, for example. So as the reagent. C2H5, you can use C2H5Cl as the reagent. C3H7Cl as the reagent for this case. Yeah, so that means originally, before they stick to the benzene ring, there is a Cl here first. There is a Cl here. Okay, before they stick to the benzene ring. And then heterolytic fission happen and so on. So something like this. You see how they generate the electrophile. Again, aluminum chloride go and attack the RCl. The R stand for the CH3, CH3Cl or C2H5. This is also R, RCl. C3H7 is also R. R is basically the hydrocarbon branch. So with Cl. So what happened is the aluminum chloride will take the Cl minus, leaving the R become R positive, which is electrophile. Likewise, acyl chloride. Acyl chloride means this one, CO something. Here is hydrocarbon branch. The other side is Cl. Originally there is Cl here. There is Cl here. So that's why we call it acyl chloride. So what happened then is the catalyst, aluminum chloride, take away the Cl minus and form this again. And this, after losing the Cl minus, it become electrophile, become RCO positive. It become electrophile and they go and attack the benzene ring. So they will form structure like this. If the R positive is attacking the benzene ring, they will form C6H5R. C6H5R is like, for example, like, okay, let's say I draw it here. If we are talking about CH3, right, then they will form benzene ring with CH3. So something like that. This part is known as R, and this part is C6H5. So C6H5R, based on our equation. Whereas this one, C6H5RCO, what kind of structures? It's something like this. We have benzene ring, then CO, R. Okay, so that is the other structures under acylation. Okay, so again, something similar happens. The AlCl4 here, the AlCl4 minus, which is formed, is just a temporary situation. So it will wait for the H plus coming from the mechanisms, the same mechanism. You know, the mechanism at the end, H plus is kicked out, the electrophile will just remain there. So the H plus will come out to find the AlCl Cl4 minus and form HCl, and catalyst regenerated. So that's why HCl is one of the product. Okay? Aluminum chloride is just the catalyst you can put up here, and then the reagent is benzene ring with RCl or RCOCl. It's up to depends on which one are we talking about. Okay. Heat under reflux anhydrous aluminum chloride as catalyst. Okay, these are all about electrophilic substitution. Okay, now let's move on. 6.6. So at 6.6 we have electrophilic additions. Electrophilic addition. So you can see something like this. C6H6 plus 3H2 becomes C6H12. So what happened is a benzene ring with double bond, and double bond react with 3H2, then become single bond. This is no more benzene ring idea. Cyclohexane, this structure, cyclohexane. Okay, so that means how they go to the double bond and just do addition, and then no more double bond at the end. C6H12, this is C6H12. Yeah, the product is C6H12. So this is called electrophilic additions. Hydrogen gas is the reagents. Temperature 150 degrees Celsius. Catalyst nickel. So this condition should be familiar, right? You learn hydrogenation in alkene, alkene to alkane. So this is just similar. Alkene to alkane. This is benzene ring to cyclohexane. It's very similar. Okay, so let's see how we apply it in this past paper. What we learned just now, and apply it in past paper. But you have to remember your AS organic chemistry. So it is related. Now, let's start. The anti-inflammatory drug ketoprophene can be synthesized from benzene via the following 5 steps. Okay, so first, benzene and become this. So what is this? COR. Okay, COR. If you still remember, we just learned not too long ago. This is acylation. Okay, COR. So you should expect something like this. I write down first. Acylation. In step 1. So if you still remember what I mentioned just now, the Cl remove away, and then the COR we just stick to it, and that is step 1. Okay, so let's work out step 1 first. Step 1. If you want to draw this, it's a bit hard because very limited space. So let us write down the formula, the structural formula. So the benzene ring is C6H5, then the COCl. Okay, this one is acceptable also. And condition, so we need the catalyst, aluminum chloride, So that is step 1. Now we look at step 2. Once you get these structures, then you want to form something. Okay, you want to form something. They give us the formula, the molecular formula, C15H14O. And you have to use it to do step 3. Okay, so how? C15. So when we say C15, right? So let's see in these structures, how many carbon are there? So this benzene ring 6 carbon, the other benzene ring 6 carbon. Then in the middle, you know, this is C double bond O. Okay, the middle one, the structure in the middle here, C double bond O. So 6 carbon, 6 carbon, 12 carbon, this one more carbon, 13 carbon. 13 carbon, and this one, 15 carbon. 15 carbon. So 15 carbon, and how to add 2 extra carbon. So you have to think of alkylation. So alkylation is to add carbon. Alkylation. What kind of alkylation? You see the next steps, it will give you some idea. You may add something on this side. Something on this side. Then after that, you add bromine to it later. You know, here no bromine. Here bromine is there. So this one we can do alkylations. Alkylation. So alkylations. So alkylation, we add a structure with 2 carbon. Something like this. RCl, RCl. Just now in the notes we have that, RCl. So the RCl that I mean has 2 carbon. 2 carbon, so you have to add it to the site. Okay, so we draw out the structure now. Okay, so you can see the additional part is here. This is the 2 carbon, 1 carbon, 2 carbon. Okay, so we write down step 2. So step 2, it will be this reagent. Okay, this reagent, I write down the skeletal formula already. Now you have to write down the structural formula. CH3, CH2, Cl, plus aluminum chloride, the catalyst, plus heat. Okay, now the side chain is added. Now we have step 3. Step 3, imagine this is ethyl. So ethyl is having a structures of alkane, all single bond. So in a sudden, you want to put a Br to it. As you can see in the product here, Br is there. So alkane, add Br, that is free radical substitution. Free radical substitution. Let me write down first. This is free radical substitutions. Okay, so we have to add bromine then. Br2 plus light, or you can write UV light. It's up to you. Okay, that is step 3. Now let's move on. Once they form this, then they have to form something which is called structure U. Structure U is what? No hints. So you have to look forward, use the future to predict the present. Okay, so this is the future. At the end, they form COOH. Previously, they formed Br. Br, now COOH. Okay, that means you need to add 1 carbon here, no? That is your AS chemistry. AS chemistry, the haloalkane. Haloalkane, you want to add 1 carbon to this part, you have to put KCN in ethanol. AS chemistry. So we have to put KCN plus heat in ethanol. So the structures here, benzene ring again, CN. And then step 5 is the hydrolysis that we learned in AS chemistry also, hydrolysis. The CN will change to COOH. So we have to use, let's say we use HCl, aqueous, heat. So step 1, to answer the mechanism here, step 1 is actually the one type of reaction. You may wondering acylation. Acylation is under electrophilic substitution. So both will be fine, but writing electrophilic substitution is safer. Electrophilic substitutions. And step 5 is hydrolysis.